When is a function differentiable? If f is differentiable at the point x equals a, this limit exists, given by your standard difference quotient. We called this value of the limit f prime of a, the value of the derivative at the point x equals a. Now remember that a plus h is some nearby point. If we were to let x equal a plus h, then as h goes to 0, x has to go to a. The definition of the derivative then looks like this. It's a limit as x goes to a, f of x minus f of a, all over x minus a. So in this picture here, we could say that this is x. Remember, there's a geometric interpretation. So this is the secant slope between the points x and a. As you move closer to the location a, those secant lines should approach this tangent line. The slope of the secant line should then give you the slope of the tangent line. Whether you're approaching from one side or the other, the secant lines all converge to the same tangent line. If you have a function that's differentiable, so let's say this parabola y equals x squared, when I talk about the origin, as I take points to, let's say, the right, and I talk about the secant line, as the lines move this way, they want to converge. As I move this way, they want to take me to this green line. The derivative of this function at 0 exists, and it has a value of 0. If we were to talk about this function, the absolute value of x, you can see that there's a different situation. For all the secant lines on the right, every secant line we take has a slope of 1. But for every secant line that we take on the left side, the slope is -1. And because those slopes don't agree, the value of the derivative does not exist. You can't have those secant slopes converging to the same value. Does this idea generalize to a function of two variables? And if it does, how do we generalize it? Well, the definition of the derivative is going to give us some clues there. If a function is differentiable, this limit exists. So this is going to hold the key for telling us how to generalize things. What we're going to do is reorganize this equation. I could subtract f prime of a, and that'll turn it into a 0. Now, because this limit exists, that means the limit laws apply. And if the limit laws apply, all of that stuff you learned from Calc 1 works. And in particular, this is a constant. So if that's a constant, that means you can pull it inside of this limit. We'll get f of x minus f of a all over x minus a, subtract f prime of a, all within the limit. Now, if I put everything over a common denominator, I'll have f of a subtract f prime of a into x minus a, all over x minus a. So I'm going to do one more rewrite to try to drive the point home. I'll have f of x subtract f of a plus f prime of a into x minus a, and all of this is divided by x minus a. Now, there's a couple of key things that come out of this rewrite. First of all, this expression right here is the linear approximation of the function at the point x equals a. What I have is that f of x minus L of x over x minus a is equal to 0. Now, since this limit exists, what this tells us is that f approaches its linear approximation faster than x approaches a, because the limit equals 0. If the limit didn't equal 0, then there's no requirement for that to happen. But the limit does equal 0. It does exist. So this must be the case. The difference between those two functions gets so small so fast that it forces this limit to exist. And the point here is that L of x is the only line at x equals a that does this. Any other line will not converge fast enough. The slope of that line must be the derivative. And that result right there gives us the clue as to how we should generalize this derivative. So here's how we are going to define differentiability of a multivariable function. We're going to let our function be a function of two variables, and it's going to be defined on some set D in R2. We will say that this function f is differentiable at the point AB, which lives in that domain D, if these partial derivatives, f of x at the point, f of y at the point exist, and this limit exists. So it's going to be the limit as xy gets closer to AB, f of x and y, subtract its linear approximation over this expression. Now, this expression here just represents the distance between those two points, xy and AB. And if the function is differentiable, this limit must exist, and it must give me 0. L of x and y is the linear approximation of the function, and it's made up of those partial derivatives at that point. So now you can see why we need these to exist. If those values don't exist, then we can't define that linear approximation. As our point gets closer to this location AB, this function gets closer to the linear approximation faster than xy goes to AB. It's the exact same concept as we talked about for the single variable point. And what that tells me is that the function is locally linear. It looks like a tangent plane near this point AB. This plane is the one and only plane for which this is going to happen. This is the magic condition. Now, geometrically, what is this saying? If I have a function that is differentiable at a point, that means if you were to pick any other points and then draw a secant plane through those other points and your point, as you get closer to the point you're interested in, the secant planes converge to the tangent plane. But if I were to talk about a different type of surface, so for example, z is the square root of x squared plus y squared. This is the top half of a cone. There's the coordinate system. There's the z-axis there. Right at that point at the bottom, we have a problem. If I were to talk about any secant plane that contains this, the secant plane has that orientation this way. We could think of the normal pointing out. So at the origin, we don't know what direction to draw a tangent plane. So the point here is that if the function is differentiable, it can't have any sudden changes in this orientation. So much like a non-differentiable function of one variable, it can't have any corners or cusps, no spikes or crinkles. So surfaces with sharp points like this would be non-differentiable. Anything with a weird corner in it would be a non-differentiable type of surface. No matter how close you zoom in, that function will always have this sudden change in the secant directions. If I keep zooming in, it will never look flat. Now, with the example that I wrote above there, call this my function f of x and y. The value of the function exists at 0, 0. The value of the partial derivative, I need to go and resort to the limit definition. The reason is if I were to use the chain rule, I would find that I would get an x squared plus y squared in the denominator. I would need to compute this, and what this would produce would be square root of h squared over h, which is the limit as h approaches 0, absolute value of h over h. If I'm approaching the limit from the positive side, this will give me a 1. But if I'm approaching the limit from the negative side, this will give me a negative 1. And so you can see that the partial derivative there doesn't exist. And that means then that the function is not differentiable at the point 0, 0. So what is the derivative of some multivariable function? So once again, we're going to look to the definition of the derivative for some clues. So our definition of differentiability said f of x and y minus f of a, b, plus these partials at the point we were interested in, fy, a, b, y minus b, all of this over that square root expression. I can rewrite this as follows. It'll be a limit, and I'm just going to ignore the specific values. I'll have f of xy, subtract f of ab, subtract, and now I'm going to make a following observation. This is a vector that contains these two partial derivatives, and that vector is being dotted with this vector, x minus a, y minus b. And the whole thing is still over that square root that represents the difference in the distances. If you compare this with the single variable definition of f prime, f of x minus f of a, subtract f prime of a times x minus a, all over x minus a. The term in front of that difference is what we called the derivative. Well, by the same token, the term that's in front or multiplying this thing right here is what we are going to call the derivative. So that means the derivative of f of xy at the point AB is this vector of partial derivatives at the point that we are interested in. Now, this vector is going to come back again later on in the course. This surface, 9x squared plus y squared plus 6x minus 3y plus 5 at the point 1, 2, and 18. The partial derivatives were given by 18x plus 6 and 2y minus 3. The partial derivatives exist at the point we were interested in, 24 and 1. This expression here is f. So the derivative of f is this vector at this point, 24 and 1. The derivative at a general point would then simply be this vector of functions, 18x plus 6, 2y minus 3, at some point xy. Now, the definition of differentiability is awkward to use because it's in terms of limits. So there are some theorems to help us understand when a function is differentiable or not. The proof of these theorems requires multivariable analysis, so they're just best stated here. The first one is very similar to something you saw in Calc 1. If your function f of x and y is differentiable at a point AB, then your function is continuous at the point AB. This theorem allows us to immediately figure out when something is not differentiable. When you have a theorem like this that's in the form if-then, there's something called a contrapositive. If you negate both of those expressions and reverse the order, the result will still be true. So if f is not continuous at the point AB, then f is not differentiable at the point AB. If you have a function that has a hole or a gap or a jump or a break, it can't be differentiable. Now, you have to be careful with the converse. The converse is when you just switch the order of them, it's not always true. If f is continuous at the point AB, then f is differentiable at the point AB. We just saw that that's not always true. When I have this cone, the function here is continuous, so f is continuous at 0, 0, but it's not differentiable at 0, 0. So this theorem is more of a test to try to help you see when something is not differentiable. The next test is much more useful. So we're going to talk about a function that's defined on some domain in R2. If the function has continuous partial derivatives, fx and fy, at points near some point A, B that lives in D, then f is differentiable at that point A, B. This is a stronger result. It says to you if you can find the partial derivatives and they exist and they're continuous, so a little bit stronger than just existing, then you are guaranteed to have a derivative. So in the context of our previous example, when I had this function 9x squared plus y squared plus 6x minus 3y plus 5, I already saw that these partial derivatives were given by the following expressions, and these are just linear, and that means they are continuous for all points x and y that live in R2. And because of that, the theorem tells me that this function is differentiable for all xy in R2. The continuity is important here. Without the continuity, I don't necessarily get the existence of the derivative.